So we assume that all of our particles are spherical to simplify some calculations. They'll all have uniform density. Throughout the Earth's atmosphere, we go through different layers of the atmosphere, and those will change in a piecewise way. And the viscosity of air is dependent on the temperatures in all those layers. We make some assumptions about heat transfer. We'll assume that the particles do not fragment, and depending on radius and other factors, the drag the particles experience are based on regime-based drag models. Also, the radii will be distributed on a log normal scale, and the velocity will be on an exponential distribution scale.
Yes, so for our first question of how we are going to be generating our particles, we are using this paper from AGU, which was basically discussing the velocity distribution of cosmic dust as it comes down to Earth or on entry. And in the conclusion, they give us some helpful bounds, saying that the vast majority of particles are less than 5 micrograms and less than 15 kilometers per second. And that they say the ZMIF is the best fitting model. So we will be following along with that as the basis of our distributions for the initial particles. And so in order to relate our mass from the distributions into our radius, we are going to be using this formula based off of our assumptions that we have uniform density and that all of these particles are spherical. And then, so yes, given that the ZMIF mass had a log normal distribution, due to the fact that they are mass and radius are proportional to each other, we can also have that we have a log normal distribution of radius. And from the graph earlier, we have that our velocity has an exponential distribution. And so you can see here in our code, this is how we are generating our particles that we will then input into our function. So now that we have our particles on entry, as they pass through the atmosphere, we're going to find that our velocity and our radius will decrease. Our velocity will decrease because drag will be fighting the force of gravity until they eventually settle whenever they become buoyant. And then our radius will be decreasing due to ablation. And for our drag, we used a heavily simplified model. We took it in two cases, where first we have a Knudsen number of greater than 1. And in this case, we're saying that there's so little air that our molecules will hardly interact. So we're basically in a free molecular flow. And in this case, we would use the Epstein model for drag. And then when we have a Knudsen number lower than 1, we will be using the standard equation for drag. And that Knudsen number is basically describing the fluidity of our environment. And then for our ablation, this is describing our change in radius. What we have is our particles falling through the atmosphere, experiencing friction, and that heat's causing us to lose mass. And due to our assumption that we have a uniform density, we can then relate that to radius as seen in our equations. So with both our equations for drag and ablation, we get these final two formulas or difference equations for velocities change and for radiuses change.
Here is our simulation. As you can see, we have, I believe, rendered 10,000 molecules, and as they approach the origin, it represents that their radius is decreasing as well as their velocity. And as you can see, at a certain point, they just kind of disappear off the graph, which we later explain. So here is the initial particles and the final destination. As you can see, they all land on this like bottom part of the graph, and even the ones that are not right on the origin or on the x-axis is extremely close to it. As you can see, like this is extremely small margins of error. So, and as you can see, there was a widely varied initial parameters here with particles with a very, very wide distribution. Here are our parameters. We're not going to touch too deeply on them because there's a lot, but each of these have been backed up by research online and papers that we found. Particle density is uniformly dense. The heat of vaporization, 6 times 10 to the power 6. 30% for heat transfer efficiency. Material tensile strength, 10 to the power 5. The radius range that comes straight from the prompt that was given from problem A with a 0.1 to 100 nanometers. Radius distribution, which is coming from our log normal distribution, the 2.5. The radius distribution, similar to that, is going to be 0.9 inches in log 10 space. Also, we have the velocity range from 0.1 to 72.5 kilometers per second. You can see that from the graph that we showed earlier. And then finally, the velocity distribution exponential, that being 8 kilometers per second. Then for atmospheric model parameters, we have the mean free path at sea level, because part of our assumption was that we're going to sea level, and that's going to be at 0.065. The sea level air density, that's going to be 1.225 kilograms per meter cubed. The air viscosity reference, that number, and then the Sutherland temperature, it's going to be 198 degrees. Then we also have the air molecular mass, that's going to be 4.8 times a really small number, and then specific gas constant for air, 0.2 kilopascals. And for the inverse function, what we did was we did a shooting method approach. Basically, what that means is that we had a target that we wanted to reach, and we basically reiterated initial parameters up until we reached a certain target that we wanted. And we built a kind of beautiful inverse function that's similar to what we had in the GIF earlier, but backwards. And it turns out to be pretty nice because we get pretty similar results when going backwards. So it was kind of confusing at first because the results that we got did not seem to make a lot of sense at first, but after some research, we learned that there was a phenomenon called meteoric smoke. And basically, what this means is that as these particles approach the atmosphere, it actually reaches a point through the atmosphere where it can't go down naturally fast enough, up to the point where it'll take years for it to reach the Earth because it doesn't fall fast enough. And it actually relies heavily on Earth's weather. And as a result, the displacement can vary widely. You can see particles that are very close to its initial position, also very far from its initial position. The meteoric smokes, the average life is about 5 years for it to successfully land. And that's the conclusion. Here is our bibliography. So, SCUDEM judges, thank you so much for listening. Have fun judging all these projects. Yeah.